Hello. So today I will be solving one question, which is about which is on the binary search tree. So let me get started. Okay. So this is my today's question. So given a root node reference of a binary search tree and the key, there is the node with the given key in the binary search tree. Return the root node reference, possibly updated of the binary search tree. Basically, the duration can be divided into two stages. So search for a node to remove, and then if a node is found, there is the node. Okay, so let me start with defining the interface and doing the data input validation. So in this question, I will be returning the delete node. Okay. So the data input, I will be given the root node, and also I will be given the key to be deleted. And yeah, I will return the root of the new tree. Yeah. So basically, this is the interface of the method I will be implementing. And okay. I just want to do some confirmation on the data input. So yeah, I will define it by myself. So root can be null. And for key, yeah. Okay, so first thing I'd like to make it clear is if the root can be null or not. So if the given root is null, which means that the tree is empty, so I will just return null. Yeah. So I will write it down. And also the key, if the key is not found, I will just return the given root, because I can say there wasn't any derivation operation, so I can just return the root node as it was. Okay. Yeah. So these are the interface of the method I will be implementing. So now it's clear. So I will work on the, let me think of this question with some examples. So the binary search tree, my understanding of the binary search tree is that when I think of a node in the binary search tree, the any value in the left subtree is smaller than the root node's value. And any value in the right subtree, right child tree, is larger than the root node I'm taking a look at. And I can say this relationship in any node in the binary search tree. So for example, the binary search tree is something like this. So yeah, something like this. So let me think with this example for now. So if the key I'm looking for is, so for example, if it is 15, the key is not found. So I will be returning the reference to the given node, which is 7 in this case. And if I'm given like 12, so what should happen is that I have to derive this node. So yeah, probably there would be some ways to derive this node. Maybe. Oh, okay. So let me change my example. So let me think with, let's say, right. Yeah, when I think of the case when I'm deriving the key 9, I will be deriving this node. So yeah, I think this is a good example. And let me think how I can derive this node. So one of the way I've just come up with is, oh, okay. Sorry, let me change my example. So let me think with this. So if I try to derive 11 from this tree, what I can do from here is that I will find the predecessor of 11, not 11, which is not 10. So this is the predecessor. And also I will look for the successor of this node 11. So yeah, this is a successor. So what I can do from here is that I will move the predecessor to the derived position. Obviously, when I take a look at this node 10, I will cut, derivate the reference from the parent 9 to 10. Then 10 comes to the position of 11. And then I will be updating the reference like this. Yeah, so this is the basic thing I can do. Let me think. So what I should do is find the predecessor and successor, and I will, yeah. Then predecessor comes to the derived position. Okay. Yeah, so basically I think it works. So in my case, what happens is that, so this one is derived and 10 comes here. So obviously I have to update the reference from the parent 7 to this node. So probably I need to keep track of the parent node while looking for this derived node. And then I will update the reference from this new node. The left should be pointing to the original, yeah, left sub 3, and the right reference should point to the original right sub 3. Okay, yeah. And one thing is I also have to take care is that if the derived node doesn't have the I mean, if it doesn't have the left subtree, the predecessor should be 7 in this case. And yeah. So in this case, predecessor. So in this case, predecessor. Yeah, so in this case, what I should do is so I just have to reference the parent node, right child to this 12. So I will be skipping the deleted node and 7 will be pointing to 12 and that's it. So okay, so yeah, that's what I'm thinking. And I'm just wondering if I should distinguish this case. So if this is okay, so let me think of this. So I will think of this later. So okay, that being said, I could cover the basic scenario I have to think of. So yeah. Let me clarify the time complexity and space complexity on this algorithm. Yeah, so actually this is already. So for time complexity, so what I have to do in this operation is, firstly, I have to find the key to be deleted. And in the worst case, it takes over log n, because I will be, to reach the node I'm looking for, in every node, I have two choices to go. And because this is a binary search tree, I can decide which way to go. So in that way, it will take log n time, assuming the number of nodes is n. So it should be log n plus. Then after that, I have to find the predecessor and successor. Yeah. And finding the successor takes constant time because the successor is obviously the immediate right child. But to find the predecessor, so I have to go to the root of the tree. Yeah. Oh, wait. But sorry, let me think of this. Let me think of the time complexity from the first place, because finding the key takes log of n time if the tree is balanced. However, if the tree is skewed, like the single linked list, I have to traverse all the nodes in the tree. So in that case, it will take O of n time. So when I think of the worst case, it will take O of n. And also to find the predecessor. Okay, so basically, you will take a look at the left child. You go down to left, and then you keep going to right as much as possible. That's the way you can find the predecessor. And obviously, if the tree is skewed like this, and please think that 2 is the key I'm looking for, or maybe 13, and the tree is connected like this, it will take over n time. Yeah, because I have to traverse almost all the nodes to find the predecessor. So finding the predecessor would take also n time. Yeah, so in total, it would take over n time. And for space complexity, it will be constant because I don't need any extra data structure to, in this operation. Okay. So let me think of this pseudocode. So first we find the node to be deleted. Basically, I will going down, to find this node. And also, as I said, I need the parent node. So it should be kept track of. It should be kept track of. And also, and also obviously here, everything is as the edge case. And from here, so I will be find the predecessor and also find the successor. Then I should do parent dot. Oh, wait a minute. Should it be left or right? Where should it be? Wait a minute. So the node to be deleted can be the left child of the parent or right child of the parent. So probably I have to use if condition to distinguish these maybe. Wait a minute. So oh, yeah. So okay. So parent dot left or right should be predecessor, and also then predecessor dot left. I will just say I will update them and yeah. Okay, so I think in this way I can find the node and delete it. So let me work on the implementation, writing the test code. So the first case I will be quickly cover is the edge case. So and also I will think of another case when to write this code, let me write. So this is node I will be using. So okay, so this is the let me rename this to root after removal. So in this case, I should guess the original root. So if the key is not found, I will guess the original root. And from here, I will be writing the happy path. So if I have the okay, so I will be thinking this case should be 1, 2, and 3, and 4, and 5. And if I remove this, so this is the happy path I will be thinking of. Oh, definitely I should check not only the root node, but also I should check that this node is deleted and the tree is changed as expected. So probably I can do something like the validation that the returned root is the binary search tree first. Then I will be checking if the given value node isn't included and other values are exist in the tree. Yeah, if in the actual real environment, development environment, I would be writing the testing framework. But yeah, for now, let me just go with this. Yeah, this is still good enough so there isn't any error while doing the operation. It doesn't guarantee that the root is removed or it is a binary search tree, but at least I can check if the code is executed without any error. So this is still useful in that sense. So let me go with this for now. Okay. So wait, I have another edge case. In line 63, because if the root node is what I should delete, actually it doesn't have a parent. So yeah. So I have to distinguish that case, I think. So let me think a little bit more if I can generalize the code design. So okay. Now I've just come up with another better, simpler algorithm. So when I delete this 11, I have another way to delete this node with the tree. Yeah, with the tree to be, I mean, binary set tree. So, okay. So when I delete this, I will be moving this 12, 13, 14, I mean, successor tree in as the child of, I mean, as the child of, as the right child of the predecessor. Yeah. And also, and then oh, but wait, in this case, I still have to reference the parent node. So, hmm. I see. Okay. Let me use the recursion here. So with recursion, I will, so, okay, I see. So the recursive function interfaces like this. So in this way, I will be returning the new root after deleting the key value. Because I will call it, yeah, I will call it recursively. So if root is none, obviously I just have to return none. And if root is key in this case, so in this case, I can think that the 11 is the given root node. So in this case, yeah, I will return root dot left tree with then I will return root dot left, which is now 9. Okay, so the good thing here is that now I don't have to take care of the parent because recursive function gets the updated child tree, and all I have to do is just concatenate, update the pointer to the child. So here, from here, I will do the recursion. So root dot value is smaller than key, which means that the key I'd like to delete is on the left child, no, right child. So I will update the tree in this way. And otherwise, I will update the rest of the tree in this way. Okay. And I can just return root. Yeah. Okay. So yeah, I think this works. And the good thing here is that I don't have to take care of the parent. So, okay. Yeah, time complexity is all the same. However, space complexity, it becomes O of n, because if the tree is skewed like the single linked list, the recursive function has n function stack, function call stack. So it will take O of n space. Okay. Okay, so with this in my mind, let me do the implementation. So this is fine, but I will know them if root dot key is smaller than key. So what I'm looking for is on the right chart, the root I updated. And if root of what I'm looking for is smaller, the key I'm looking for is smaller than the root value. So it means that the key can be in the left subtree. Okay. Then here, root dot value is key. So remove this root. So what I can do is okay. First three, I will find the predecessor. And also I will be finding successor. Oh, actually successor is right immediate child. Okay. So when I guess the predecessor, I will, yeah, okay. So I will, move the successor tree as the child of this predecessor. However, if the predecessor is none, it isn't possible, and it should be treated as a different edge case. So, okay. If root dot left is none, in this case, there isn't any predecessor. So in this case, what I should do is, because I don't have any predecessor of this child, I just have to return the successor. Yeah. And otherwise I can find the predecessor. So I will put the successor to the right subchild, right child of the successor. Then I will return this predecessor. No, I will return root dot left. Yeah. Okay, let me double check. So if there is a left child, I will just return root dot right. And if there is a root dot left, I can find the predecessor in the left subtree. So then in that case, I will put the successor tree as the right child of the predecessor, and I will be returning root dot left. Yeah, because I want to remove the root node. Okay. So here, then I will find the predecessor in this way. Okay, root dot left is non-current. So as I said, I will go to the left once, and then I will keep going to the right as much as possible. And I will return current. Okay. Okay. So let me walk through this code with this example, 2, 1, 3, 4, 5. So now the root is 2. Oh, wait a minute. Okay. So firstly, I will call this root of the removal with root 2 with key 5. So in this case, root is not none, so it's okay. And in line 116, root dot value, which is 2, is more than key. Yes. So I will go into line 117, and root dot right is root after removal root right key. Okay, so I will update the right child, and then I will return root. So yeah, theoretically, this original root is returned in the end after updating the right child. So with this keeping in my mind, I will think what happens in this. Yeah. Oh, sorry. Because I want to remove node 3. It should be 3. Okay. And here, because root is yeah, root dot value is key. I will go to line 112, and here I will check root dot left, which is 4. So this is a known, so I will go to 128, and I will get the predecessor. Yeah, I will skip going into the method, but assuming that I get the node 4, predecessor.right is root.right. So now this 4 has the child 5 as the right, yeah, child. And then I will return root.left, which is current 4. So what happens is that this method returns this. Okay, and so this is concatenated as the child of 2. So the return tree should be something like this. Okay, so what I can say from here is that this is the buried binary tree, and also key 3 is removed, and also there isn't any other key which has been removed. So this is okay. So I can say this case passed. Now, because now I'm pretty sure that this code works, I will run this code. Okay, good. So, yep, let me finish my coding practice today. Bye.